Good afternoon, everyone. Hello, welcome. Welcome to Luyang, Senior Postdoctoral Research Fellow at Harvard Biomedical Informatics. He was trained at the Chinese University of Hong Kong in computer science and engineering. We're very thankful for him to come and spend his time with us today. It's an hour lecture. We have it on both on Zoom and in person, and we're going to be talking about multimodal medical AI development and deployment.
Thank you so much, George, for the introduction, and thank you everyone for having me here. It's a great pleasure. So basically, the title tells you a lot about my research interest. So to begin with, what an amazing medical AI world we're now living in. We now have more than 1,300 FDA authorized medical devices with AI ML capabilities. We have more than 86 randomized controlled trials on AI in clinical practice. We have these major AI companies launches their AI initiatives for healthcare. And when speaking about medical AI, there are three key factors that I'm mostly interested in, including the medical data, the algorithm development, and the evaluation environment that are proposed to challenge these models and further deploy and develop them. So if you look at the field, this field has gone through a shift from developing models focusing on single data format on narrow tasks all the way to models that are capable of integrating multimodal information and perform versatile and dynamic tasks. And that basically tells my research journey, where I start my PhD thesis with learning from imperfect medical data, and then spend some time at my first half of the postdoc career on multimodal medical AI development, and then multimodal medical AI deployment at Harvard. And today, I want to share three key works from mine, which are basically first, the development of multimodal medical AI that understands different modalities, and then the deployment of multimodal medical AI that delivers outputs effectively to the patients, the stakeholders. And three, development of a medical AI sandbox that offers dynamic and safe deployment. So to begin with, the first work, multimodal medical AI for breast MRI diagnosis. Breast cancer has the number one incidence rate and number two mortality rate among female cancer across the US. And breast MRI has the highest sensitivity among all kind of imaging modalities before biopsy, and it's often recommended for high-risk women. So from one of our early study, we have reported a sensitivity of radiologists of about 98% and about 60% of specificity. So reading breast MRI is, however, challenging. Breast MRIs are multi-sequence, meaning there are different ways for that imaging. And typically we have, for example, dynamic contrast enhanced MRI, the DC MRI, and DWI, the diffusion weighted MRI, and T2 weighted MRI. So these are different modalities. And the radiologists have to look from sequence to sequence to extract this volumetric feature. And that is not enough. They have to look through the DC MRIs to extract these kind of kinetic features. So DC MRI are basically T1 MRIs taken from different time points after a certain agents injected to the patient. And the radiologists have to find a really typical point inside that lesion and then draw a time to intensity curve. And that curve there basically tells a lot about the malignancy status. So after all that, then it comes to the reports. They have to integrate these findings, the volumetric ones, the kinetic ones, into a BI-RADS assessment. And BI-RADS assessment is a score system consisting of 7 different scores. 0 means incomplete imaging, 1 negative imaging, 2 benign findings, 3 probably benign, and 4 suspicious of malignancy, 5 highly suggestive of malignancy, and 6 is a knowing malignancy after biopsy. And the recommendations are made then after these BI-RADS scores are given. So basically, a finding of 1 or 2 or 3, probably there's no biopsy recommended. Finding of 5, biopsy recommended. Finding of 4, discussion between patients and physicians. So this is hard. And our question would be, can we develop a multimodal medical AI for breast MRI? And there are 3 questions we want to answer. First, how to integrate multi-sequence information. 2, how will the multi-sequence information help? And 3, how do we deal with missing modalities if there is any? And to do that, first of all, foundation models, that's the solution to a lot of questions. But foundation models have its promises and also the gaps. In terms of promise, they have powerful transfer learning capability during the fine-tuning stage. They have extract a large representation learning from the pre-trained data. But also there is significant domain gap in between the foundation models that we have nowadays to our specific problem, the multimodal volumetric medical image. So how do we build an AI architecture that utilizes the foundation model parameters while also enables multimodal fusion? First of all, like every AI research would do, we do a sort of little downsampling using our small CNN models, downsample the kind of dimension into acceptable dimension. And then we propose this sparse mixture of modality experts for kind of unimodal learning. So the key idea here is we fix the most parameters of this adapted foundation model, and we insert certain sparse experts there. And they are typically just a few layers, very simple structure, very lightweight. And specifically here, we ask each expert to take care of a specific subset of the tokens. So for example, expert number 1, you are handling the tokens from DCE. Expert number 2, you're handling the tokens from DWI. Number 3, you're handling T2. So with that, we kind of inject this kind of unimodal learning capability with each one of the experts. And then after several layers of such structure, we want to learn multimodal fusion. So here we propose another structure called soft mixture of modality experts. And more specifically, it shares kind of similar structure with the sparse ones, only that we have this softer MOE structure, and it looks like this. So this structure basically tells that if we have M tokens as input, let's call them X, and I have a learnable parameter phi. With X and phi, I can have a transition matrix. I take the first dimension softmax, and I can use this transition matrix to combine these M tokens into N slots. And now these N slots becomes multimodal tokens. And they're basically linear combination of the input unimodal kind of tokens. And what we do next is we have different experts for these different slots. So basically, every expert will learn a kind of fusion strategy there. And after that output, we take use of that X5 transition matrix again. Use that, take a softmax at the second dimension to decompose the N number of slots back into M number of tokens. So combine these two different layers, we have our final model, the mixture of modality expert model, MOME. So what it does is basically at the first few layers, we do unimodal learning. At the last few layers, we do multimodal learning. And also it offers kind of parameter efficient fine tuning, whereas basically we don't have to train the large scale of the foundation model parameter. We only have to train a small subset, which are the lightweighted experts there. And it not only provides a fast convergence, it also provides, save us some computation costs as well. So how do this model perform? First, we conducted a reader study comparing MOME's performance against 6 radiologists. And from that curve, we can basically tell 5 out of 6 radiologists' performance lies on or even under the curve of MOME. That means there is at least one threshold we can find to tell this model is comparable or even better than the radiologist. And second, it turns out MOME performs robustly across different hospitals. We have our internal testing set, column 1, when I have 2 external validation sets, the 2 other columns there. And worth noticing is that the third column, that hospital has a significant domain shift from the previous 2s, but still we have about 80% of AURC. And it also turns out this model performed robustly across different subgroups. We have the subgroups divided by different risk factors, for example, the BI-RADS, the BPE, the age, and also subgroups by the magnetic field. And we can tell that MOME perform robustly across different subgroups, except for the BI-RADS 4 subgroup, which is kind of in the middle of malignancy and benign lesions. So we can also interpret this model, interpret where does it look like. And specifically, no matter what a kind of breast MRI is given to this model, either it's a malignant MRI or it's MRI contains benign tumors, by saliency map, we can tell where MOME looks at those specific lesions. And the next question we want to answer is whether we can deal with missing modalities, if there's any. So it turns out this kind of structure can deal with missing modalities quite good. If we don't have, for example, DWI and T2, we can remove their downsampling CNNs. We can also remove the sparse experts corresponding to them. And that soft MOME structure doesn't prevent us from inputting any combinations of the tokens. So with that, we can do a lot of interesting things. One of the interesting things we can do is that we can input different combinations of these modalities into that model and try to figure out the contributions of each modality. And here is what the contribution looks like. So by Shapley value analysis, for example, if there is a malignancy in that breast MRI, and we made a positive prediction, we can tell that DCE makes the most contribution, followed by DWI, followed by T2. And if there is a benign lesion, we can tell that the most contribution are made by DCE, followed by T2, and then DWI. So we can also interpret such Shapley value in the group level. And basically, the group level tells us if a positive prediction is made, the contribution are mostly made by DCE followed by DWI. And if a negative prediction is made, the most contribution are made by DCE followed by T2. And this is well aligned with the clinical literature. And how does MOME perform as a decision support tool? So basically, here we run a decision curve analysis, whereas we compare the net benefit of either we should do a biopsy based on the AI decision versus sort of default settings, biopsy for all, biopsy for none. So it tells us across a long range of threshold probabilities, this AI decision has higher net benefit compared to others. So up to now, we have talked about developing these AI tools for clinicians, and there is one audience who is silenced and underserved, which are the patients themselves. And we want to develop it directly for the patients themselves as well. So this part, I'm going to introduce our work on patient-friendly video report generation. Specifically, why should we do this? First, there are studies telling us patients are struggling with understanding the radiology reports. There is a study back at 2017. They report a kind of comprehension score surveyed by the patients, and its average is about 2.5 out of 5. And also out of the common problems, about 60 of the surveyed patients reported that there is unclear or technical language within that report. And about 10% of them report that the radiology reports they received are too long. So if we take a closer look at a radiology report, you can basically tell this is a kind of communication in between professionals. They're not written for patients. And there's a lot of technical jargons and a lot of negative findings. And this is not because radiologists are required to write these kind of negative findings, that kind of no findings. This is because they're required to write really comprehensively, to inspect really comprehensively. So is there a second kind of format that can help us deliver such information to patients? It turns out it does. So we can do a video report, and there is tons of research on that kind of direction using kind of handmade video reports or handmade clinical notes representation, send them to the patients and show improved engagement as well as improved understanding. But our technical challenge here is, can we do this with AI? So to start with, we first use an LLM to extract the most concerning findings, which are the abnormalities inside these long radiology reports. And I'm only showing a part of it. Ask the LLM to turn it into a sort of more comprehensible format. And then using a talking avatar tool to translate these texts into a talking avatar, which will serve as the interface for that narrative. So that is done the part of explaining the reports. Second is how can we explain the image? Because reports are basically descriptions of the images. And if you don't know what findings is located where, you don't know what's going on within the human body. So what we do is we seek the help from the segmentation models in the medical image segmentation domain. And specifically, this kind of models, they can take in a pair of just a CT and a name or text of a specific organ. And then it gives you a segmentation map corresponding to that organ. So if I ask you to segment the aorta, it segment the aorta for me. What we do is we not only segment that aorta from a patient CT, we also retrieve a normal CT scan there, do a segmentation, and use that as a sort of comparison to show what will happen if there is no such findings. So lastly, we now combine all the previous generated results into our video. So we have the patient CT segmented to tell what was found, what does it mean, how does it look like. We have the normal CT segmented to tell how does a normal scan look like as a comparison. We then have the 3D rendering of that organ to tell how does the organ looks in 3D in the holistic view. And I have the avatar to explain everything. And here is what the video looked like.
Your CT scan shows something called ground glass appearances in both of your lungs. This term describes areas in your lungs that look hazy, like frosted glass, which can happen when there's some inflammation or fluid in the lungs. In your case, this pattern is typical of viral pneumonia, which is an infection in the lungs caused by a virus. In your CT image, you'll notice these hazy, cloud-like areas in both lungs, especially around the edges. They aren't as clear as the rest of the lung tissue, which is why they are called ground glass. In a normal CT image of the lungs, you would see clear, dark areas representing healthy air-filled lung tissue without any hazy or frosted appearances. The lung tissue would look uniform and consistent throughout.
So we call this system Rex play. And the next thing we care about is how do the stakeholders think about the Rex plane generated videos. So we conduct a reader study with radiologists, 5 radiologists. We generated 10 videos, ask each one of them to watch the videos and provide us with some feedback. So with that, we have collected 50 data points. We ask the radiologists to rate the video content as well as their Sure.
Just a question about what it's really rendering parts. Are you also rendering based on the individual 3D scan, or is it general 3D scan, 3D rendering form?
Yeah, this is personalized for that specific patient. Yeah.
So personalized, but without the findings.
Yeah. So we can basically, so here we only segment the organs out and rendering the organs. But later I will show another improved version of this, which we render not only the organ, but also the finding.
I can already that question is for the normal scan. Is that coming from another person or it's the same individual, but you generate a narrative cases?
Sure. Thanks for the explanation. So that's retrieved from another person. Yeah.
The reading is fine.
Yeah.
Body different between
Yeah.
people. But okay, that's
Yeah, but I think with the improvement of generative AI, someday we will see that from the same person, but now, yeah, without anything, yeah. So we have this user study, and they are also giving us kind of free text suggestions, and here is the result. So first of all, most of the videos are deemed to improve understanding, including the comparison with normal CT scan, whether the video comes across as conversational with the patient, whether connecting the explanation with the image help improve understanding, whether the explanation of the report is easy to understand, as well as
understanding is being assessed here.
the radiologists.
Perception of how it would change patients.
Oh, yeah. So I think the second one. Yeah.
So this is to help patients.
This is meant to help patients.
based on biology?
Yes. Yes. First of all, they are the closest to their patients. And second, to deliver this kind of things to patients, you know how IRB goes. Yeah. And also, they think Rexplain delivers correct information in terms of most of the videos localize the findings to appropriate organ, sufficiently reviews the findings with the patient, explain the findings in a way that can be understood, and also correctly identifies the important findings. And also, we are super interested in whether there is kind of potential interest in.
Sorry, I don't know if you're going to get to this, but there are some non-zero strongly disagree.
Yeah.
Will you talk later about where those came from and what is it that they disagree with? Or
Yeah, so basically, some of the strongly disagree comes with the first of all, hallucination from the LM, and second, some of the segmentation. Because if you are looking for a very specific finding, and if you are just rendering the whole organ, there is not much information in that part. Yeah. So regarding the potential interest in using your Explain, so there are some positive feedback regarding whether they're comfortable walking the patient through the video. But when it comes to whether they are comfortable showing the video to the patients without the supervision, yeah, there's a lot of hesitations, of course. So from the potential clinical usage from the free text feedback, one of the radiologists said probably immediately use this before the physician sees the patient, and followed by in-person review for like question answering to secure its usage. So security is really important. And also we can make these available with kind of every image that is by one of the opinion of the radiologists and look for improvements in terms of patient engagement, follow up, as well as whether there's decreased burden on the referral physician. So just to follow up Lina's question, we are super curious about whether the improvement of technology will lead to improvement of user feedback. So the first kind of thing that we're really curious about is whether we can make these segmentation models to be more precise. So now if you look at this model, we won't go into the detail of the architecture, but if I ask it to segment the left lung, it gives me a left lung. What if I asked it to segment a peripheral consolidation in the left lung? Can any model do that? And it turns out there's no such model can do it really well. And we have run a benchmark study comparing the state-of-the-art models. And so in order to increase this, improve this line of research, we have open source this data set called Rex Grounding CT, including more than 3,000 non-conscious CT scans. Yes.
Or with that part, with the previous part,
Yep.
would you say it's more like a data problem or the model issue? Because I worked with CAD's description of scans before.
Yep.
Sometimes like what I found was that clinicians tend to be really conservative and then it's not completely descriptive. Do you think this is an issue that's fundamentally cannot be solved unless the data is like has higher quality, or is it something that can be solved upon?
That's a really good question. I think the problem really comes from two parts. Part one is, as you said, from the data itself. And what we do with the data set is that when this kind of lesion is really easy to find, we have the segmentation mask. If it's not easy to find, we have like a rough mask or like a bounding box there. So, and I think question two is actually also related to kind of models. So basically, when you look at the previous structure of these kind of models, they are actually these kind of text encoder, query decoder, you can treat them as a sort of mapping functions to map or classifiers for each of one of the classes, but they don't generalize. So you know what a left lung is, but you don't know the relationship with left lung and right lung. Yeah, thanks. Yeah, so this is the Rex grounding data set, and we also hold a leaderboard there. If you search rexrank.ai, you can find a lot of data sets released from our lab, and Rex grounding CT is one of them. So the next question is, can we improve all kinds of different technology? Would that lead to improved stakeholders' opinion? It turns out we can. if we can have better LMs, if we can have more vivid avatar, more precise segmentation, we can have better videos. And this is what a better video looks like.
This examination found a hazy, inflamed spot in the left lower part of your lung. This suggests that there could be an infection, possibly related to COVID-19, causing these changes in that area. At the rendering window, there's an orange-colored spot representing this finding. In your CT image, the affected area looks cloudier and denser than the rest of the lung tissue, forming a faint cloudy patch in the outer region of the left lung. In a healthy CT image, you would not see these hazy patches. Instead, you would see mostly dark spaces representing air with a few thin white lines and dots representing normal blood vessels.
So how will this change the radiologist's opinion? It turns out they think the improved direct plane can deliver more accurate message. And here's the change of the scores. A lot of greens here. And they also think there's more potential usage for this kind of system in terms of whether working through their patient through these videos or whether they are comfortable in providing the videos to the patients before their visit. So basically, this is a proof of concept study. And what we want to tell really here is with the improvement of the different kinds of generative AI technology, there is a potential for us to create a self-healthcare pathway after the patients receive their clinical notes, before the patients going to see their referral physician. So, here is the overall change of score. I won't go into detail about that, but the next question, after we build these specific tools for clinicians, for patients, now we're at the generative AI world, the agent world. My question would be, are medical AIs ready to get into the hospital? Specifically, I mean the medical LMs or medical agents. So I will share with you our work on clinical environment simulator development. So to begin with, let's take a look at how we currently evaluate our clinical LMs. Basically, we have exams, we have case vignette like this, and then we have options to your LM. And take a screenshot or take a picture, whatever. Every LM nowadays can answer this really, really good. The answer is B. And but this is not closer to the real world. The real world is dynamic. And the previous case vignette may look like something like this. A man walks in holding his chest. Two other patients are already waiting. You ask about his pain. He says, it's probably nothing. I just feel weird. And he's sweating, but insists he's fine. And while checking his blood pressure, an alarm goes off for another patient in the next room. And his wife mentions, oh, he took some pills earlier, but I don't know what kind. She can't remember his medical history. And his pain suddenly gets worse. He looks pale. And he asks, I really need all this. I have a meeting tomorrow. What do our clinical LM do? Do we have an environment for that? So you can basically tell there is a gap in between the static exams to the real world environment. And for that, can we do something like this? Can we build a dynamic simulated environment for pre-deployment evaluation? So let's think about what makes a dynamic environment. A dynamic environment should have awareness of time. Things are moving, and then it should have kind of resource constraint. Of course, I always have a long line outside my CT room. Of course, I have shortage of my ED beds, of my nurses. And for that, I have competing priorities. So I'm doing multitasking. I have to think about which patient I have to go first and then to the next one. And the states are evolving, the patient states, the resource states, the hospital states. And because of that, every information gathering, every decision-making are now sequential. So how do we do that? First of all, we think there are two really important things we should build for this. First, the patient engine, second, the hospital engine. And once we have these two engines, if we can build such a loop, the engines generate states change. States becomes observation to an end user, being either a human or an AI, and that user inputs something to that environment and generate the next stage from a loop. That will be our environment. So how do we do that? First, how do we simulate the patient involvement? So let's take a look at a typical EHR. And EHRs, they're not just static records of a patient's history. They're actually patient's journey within that visit. So if we can unfold this EHR along the timeline, this basically tells us what happens from a time point of view. And is that enough for a simulation? That is not enough. You have to consider what ifs, right? What if an action goes off script? What if I order something that hasn't been recorded before in this EHR? And also, what if I missed some critical actions? The patient could deteriorate, and then you have to come back to this patient and do something else. So what we do is actually we use the current LMs and first input the EHR to the LM as a sort of grounding information. And then we ask this LM to play as a simulator. And as a simulator, what you receive as an input are actions, and what you generate are reactions. So actions would be the time advancement from, for example, time 1 to time 2. But of course, for LM, we have like turn 1 to turn 2. And then we have lab tests, image tests, vital check, history taken, physical examinations, and interventions such as medicine and procedures. And the reactions will be the vital changes, the testing results. And here are several rules that are really important for us to build this kind of simulator. So first, if an action exists in that instruction, you should return recorded results or as plausible as possible to that grounded results. Then if an action does not exist in the instruction, return plausible results that are consistent again. And if the critical actions are not met, the patient should be considered whether or not to deteriorate. And sure.
I'm just curious. Increasingly, there are sort of direct simulators of the raw EHR data that have been built in sort of a variety of settings. Why use an LLM over something that's simulating in the sort of raw structured EHR space for your patients? And
I think the basic question, the basic bottleneck we're facing before is how to generate the what ifs. And we basically think LLMs are one of the good methods to generate these actions that could go off scripts. And we do have in the next few slides show how we evaluate these kind of generated results.
I have a similar question.
Sure.
Would this be enough, like LM plus all these actions, or do you need a stronger like model or method that has like stronger inductive bias?
I think basically, so in the next few slides, we will see that the current LMs, the general ones, they can generate mostly plausible results. But I still think there are room of improvement if we can have a chance to train a second model. Yeah. Okay. So how do we evaluate such generation? So basically, we first can do a sort of assessment and then compare it with the recorded EHR to see whether the generated results are within the expecting range. So that creates the first kind of consistency check. And then we can do sort of interventions to this patient and do a second round of, did I hear something? Okay, the second round of assessment and have the second round of consistency check. So with the help of our medicine experts, we create thousands of these kind of consistency checks. And here is the overall results. So basically, an overall pass rate is about 89%. And it tells us the current gender LM can generate mostly plausible results there. Sure.
so when you say this consistency check, how does that actually work? Especially because you're deviating from the actual record, right?
Yeah.
So after a certain amount of deviation, you don't actually want consistency anymore, and it's not clear sort of when that would happen, right? So yeah, what exactly does this consistency rate mean?
Yeah, I think probably consistency can be used with another word, but what we do is after certain generations, And then we have an expected range there. Like you give a medicine and what you would expect that to happen, what you expect the events. And actually we check.
Or who generates that expected?
A human generated. We first generate by LM and human do like a sort of check.
Okay, so the consistency is human assessment of consistency.
Yes. You can tell it in that way. Yeah.
And then is there anything that you like alternative strategies that you compare against? Because with a metric like plausibility or consistency, it's always a little challenging because humans don't actually have to do this task normally, right? Like doctors are not trained to look at fake medical records and see how realistic they are. So maybe you could take a completely sort of random patient essay generator and get it. I don't think this is likely, to be clear, but maybe you get sort of similar numbers. So do you compare this to sort of other styles of generation to suggest that this is actually sort of a meaningful evaluation metric, or are we just sort of assuming the humans are sufficiently good judges of?
Yeah, I think the key problem here is that we're not trying to build something that is, perfectly predictable, can predict perfectly of the patient's next status. Then it's not just a generator, it's now a predictor. What we want to do is to generate average results so that basically we can tell this is plausible and making this kind of patient engine from 0 to 1 first.
Yeah, no, sorry. So I guess I see that makes sense, and I see why you're responding to my question that way. But I think I could have been clearer. I recognize that you're not trying to make predictions from these, but in order to understand, is this generation strategy, in order to understand, is this number, this plausibility something that we should take away from? We sort of need to know, like, if humans are not good at evaluating this task, then these numbers do not tell us that this is a good model for generation, right? So you could, for example, try something that everyone would agree is a bad model for generation and verify that humans score this as much better than that to provide some additional validity to the actual metric you're using here itself, right? Because, maybe humans are, going to judge things as being realistic on, it's sort of like text generation. Maybe they'll judge something as looking like good text if it's grammatically correct, even though it's medically inaccurate, right?
Yeah.
Those sorts of deviations. So do you have any sort of additional evaluation studies on the metric that sort of look at different comparisons or try and break this down in different ways?
We don't have more fine-grained checks like this, but later on we do have humans to go through sort of virtual shift and ask for their experience during that virtual shift, asking for, first of all, does all the contents generated in your virtual shift make sense based on every actions that you have input? And second, how do you think of the system itself?
Great.
Yeah, thanks.
I guess probably a follow-up question relevant to Matthew's point. So here you're kind of assuming, what just mentioned, that humans have an expectation about a certain number of rules, basically. Oh, if this happened, a patient may have a range of something like that. If human can write out those rules explicitly, then you can just generate based on the rules. You don't need to have a language model generating it and then checking it. Or if in another way, if you have a random generator, generate a bunch of things, and let human do the filtering of like, okay, remove those unplausible cases. Will that lead to similar results? Like, I guess what I'm trying to understand is like the benefit of language model, or again, relevant to the metrics, trying to define.
Yeah, I think first of all, in terms of using large language models, is that we can simulate these returned testing results similar to what will be written in a report, and that will make it look like more high fidelity sorts of. But in terms of evaluation, I do agree that there should be more fine-grained evaluations in terms of showing us not only the consistency, but also something that could exceed the human capabilities. Thank you. Okay. So after we have built this patient simulator, the next thing is to build the hospital simulator. And specifically, I'm talking about the resource constraints. So we have these sort of queues, and you have limited number of CTs, limited number of beds, nurses, all of these kind of stuff. And then the order starts passing by to these different resources, and patients start to queuing. So with that, we have the two engines. And the next question is, how do we synchronize them? So basically, given a series of user actions through the timeline, we can first input these actions into a hospital engine so that hospital engine start to wait for a certain period of time to execute that. A previously available CT now becomes unavailable. A previously unavailable room now has a queue outside, has a line outside. And then after a certain turnaround time, these orders start to be passed to the patient engine. And the patient engine starts to generate, for example, vital changes, for example, the testing results. So one last mile is how do we bridge this kind of results to our users? So what could be better than if you really have a EHR interface? Right now, we have a patient track board. You can see your patients arrive, patients discharge. You then have a specific individual patient EHR interface where you can see the returned results, the vitals of this patient, as well as placing orders, for example, the test meds procedures. And with that, we have built our clinical environment simulator. This is a generative interactive work model for medicine. Basically, we have built the loop that we described before, where the user input actions, actions goes into engines, engine generates states, states becomes observation back to the user, next turn.
How can you handle a team-based environment of care with this?
So I think you now can have multiple multiple users, and they share the same results.
And they share the same
resource. Yeah.
You mean in the hospital engine?
Yeah. So they share the hospital engine, but they kind of interact with different patient LMs. Just to imagine that different ED physicians are handling different cohort of patients.
Well, you'd also have other types of clinicians as users as well that are doing other things for the patient.
Oh, so for now,
what you're describing is multiple people doing the same job.
Yeah.
But the teamwork means they have dependencies, there's a workflow, there's information flowing between them, and they generally do different things.
I see. So what I was describing is basically imagining like you have different ED physicians, but I guess you're also mentioning like stuff like nurses. Yeah.
Doing different things, making different decisions for actions that end up having dependencies on.
So for now, we are assuming the end users are only ED physicians. And for other kind of roles, for example, for the nurse roles, we're kind of using another LM to generate sort of triage notes or generate some kind of consulting results from other departments.
In the future with this architecture, would you be able to incorporate other users that are also engaged in activities? Could it scale to that is my question.
I do think so.
You don't have it.
Yeah, I don't think so. Sorry, I do think so. But what I think is that there is definitely more complex layers there that we should build, but I don't see anything that could block us from building that. Thanks. And with this CES architecture, there are three things that we can offer, which the previous benchmarks cannot offer. First, the temporal reasoning under evolving constraints where delayed diagnostics could lead to patient deterioration. And second, the resource-aware decision-making, where aggressive workups for one patient could exhaust capacity needed by others. And third, operational resilience through different adversarial testing with simultaneous emergencies and system failures. So we can always create these different kind of hospital scripts from, for example, training scripts to daily routines all the way to code black disaster. Yeah.
Oh, sorry.
Here, and we had a bit of a discussion before, is that there seems to be an assumption again that there's a model being deployed in the clinical settings. But the question here is, I mean, depending on how you build a system based on the model, the response to how inference is presented, how much it's contextualized in other data, may be completely different. So how are you accounting for that? Two different, same model, two different software packages that utilize this model, designed different.
Yeah. So I think that that might be the next level, but here what we are mostly curious about is how can we actually have a sort of medical agent there that can perform the whole EHR workflow.
So you talked about how you evaluated the patient simulator, but I think that the hospital engine is also something that could be more or less accurate to how the real hospital works, even in the context of sort of normal operations, outside the context of the deployed model, although I agree with this point. Did you assess how realistic the hospital simulator is? And did you look at like sensitivity analysis of how much the efficacy or the sort of reliability of the whole system as a sandbox in the setting is dependent on how reliable the patient simulator is and things like this?
So we do have plan to do that, but here what we have is a kind of user study. I don't know whether the slides will show the evaluation on that part, but basically when we show this system to the users, their feedback, because we're interacting with physicians, they were like, we don't care about these capabilities. It's somebody else's job. So that is why I was talking with Sarah this morning that we really require somebody who really knows these operational workflows, tell us how do we build a hospital engine as a high fidelity. Yeah, thank you. So here we show a video of one of our collaborators interacting with that EHR workflow. Whereas you can basically see these results and do some orders, the tests, the meds, do your consultation, and then go to the next patient. And of course, the time is moving by as a sort of turn-based. So how do physicians think about this system? So we have run a kind of user study with 10 participants, including 7 ED physicians, 2 internal medicine physicians, and 1 neurologist. All of them have rich experience works in or with the ED. And we asked them to do sort of virtual shift on randomly generated scenarios, ask them to rate the system fidelity as well as their user experience after their virtual shift. So here are some highlights. Basically, they think there are high fidelity of patient progression and treatment responses. That basically is related to the generated results of the patient LMs. And then they found there's sort of strong realism in experience in terms of multitasking, in terms of the resource constraints led competing priorities in terms of even psychological pressure. And of course, in terms of time flow, there is sort of a lower score because we're doing in a turn-based simulation. It's not in real time. So, but for that, we now can introduce several new dimensions for evaluating our AI agents, especially medical agents. So first, to our sequential diagnosis and sequential decision-making regarding disposition. So these are some kind of ability you can train your AI model with just EHR records. But then we have 2 other dimensions, the critical actions, whether certain critical actions are taken for treating and diagnosing the patient, as well as how timely these actions are. So we do here is the demonstration of one of our AI agent running that hospital or the ED. Do a HMP, check the results, order the meds and tests, take some time for thinking, of course, advance the time, check the result again, and put in diagnosis, discharge summary, and discharge the patient, the whole workflow. So how does the current AI agents perform? We actually have compared the 3 state-of-the-art coding agents, actually, the Cloud Code, Codex, and Gemini Clee. And you can basically tell, if you look at different color bars, they all have quite good, not quite good, but best performance in terms of diagnostic accuracy, in terms of disposition accuracy. But when it comes to workflows, such as critical actions, such as timeliness, there is lower scores overall. That means these are the dimensions that we should work on for our future AI agents, especially when they are.
So understood how the hospital engine would take care of resource constraints.
Yep.
Have you considered how our data quality in EHRs, the reality of it is not that great. We're missing data and sometimes wrong data. So have you thought about that? And would that just be, to run the simulation and test it out, or other considerations?
I think this is a fascinating idea. Definitely we can inject certain noises into that LM generated results. But currently we are focusing on the sort of 0 to 1 thing. So, but definitely I think that's a good direction to work on.
No, go ahead.
Have you tried? Well, so you're comparing multiple models between themselves. Have you tried running it against it?
We're doing it now.
So am I correct in understanding that in this graph, you're using a model or sort of model agentic work, interface, and may spawn sub models sort of under the hood for different tasks to do the entire management across multiple patients in the context of the hospital workflow and sort of everything all at once?
Yep.
So I feel like that doesn't seem like a very sort of realistic way that you would want to use models in practice, right? Like, it seems, I think it's a great gap to identify that we're testing them on the sort of static cases of patients, but also, why would you have the model that's running on patient 1 also be responsible for scheduling something for this patient way over here in a totally different area, right? There, I recognize there's a cost sort of performance trade-off here in some sense, but I feel like reducing it to a single number like this seems maybe too reductive.
Yes, next slides. So you're pointing out to the next slides. Basically, we do a comparison in between. We ask one model to take care of multiple patients in parallel, and also ask the model to take care of the patients one after one, focusing on one. And here is something really interesting. I would expect that the critical action dimension as well as the timeliness will decrease, but also the diagnostic accuracy as well as the disposition accuracy also decrease. That means this kind of competing priority, multitasking, is not only challenging for a human, but also challenging for AI agents. And I also believe that in the future, we definitely should have a team of agents inside when we deploy them, not one for all. I hope that.
Yes, no, that's fine.
Yeah.
Quick clarification, here's the average results of the 12, like assuming for the model with the dashed lines. Are they for average results for 12 patients?
Yeah, so these are average results for 10 scenarios, and each scenario contains 12 patients.
So that means in your dashed line, that case is you're able to call language model 12 times more compared to the one on the solid color.
Yeah.
So I mean, the delta came from the multi cases versus more token or like more chances for language model to think or something.
Yeah, I think we will have that kind of analysis later, but I do think there are actually, if you ask it to take care of multiple patients at one time, it might use more token.
What if I call the model 12 times with the same 12 cases? Because you have seen recently, if you copy paste your prompt 2 times, double, just like double, it will probably do better because now the model, the decoding of the token have future information because you do it's the information, right? So I don't know, maybe.
I think that's maybe that's something because now we are only able to have these AI agents now. And we really want to explore what are the best kind of, AI teams we can build in the future. Yeah.
Back a little bit from all of this, you were asking how well an AI physician autonomously would perform managing patients in the hospital. I'm just wondering how realistic and interesting this question is. How likely is it that we will have AI physicians running in a hospital? And whether a more realistic question is, how would AI something work together with human clinicians in a hospital? And how can you simulate that? How you can evaluate it in a simulated setting? whether it's not a team of AI physicians, but it actually is human AI teams that work together?
Yeah, that's a perfect question. Actually, also kind of my future direction. And also why I think HCI is such an important area is because we actually also don't think we should have a autonomous AI there. They should be semi-autonomous. And they're just like autonomous driving, there should be different levels of automation for our medical AI agents. And I think that direction is fascinating to work on regarding how do we build these safeguards for our agents? How do we create this sort of interaction in between, for example, my AI resident and the human supervisor. Thank you. Okay, so with that, I want to share a little bit more about my future vision. Definitely I will work on something in my future world, a smart hospital. First of all, our AI teammates that will include these specialist AI tools that are specialized for certain clinical decision support, scientific finding, also AI teammates that can really work within the EHR workflow. For example, the sad story we learned from the AI trials of AI stethoscope, where when you use the AI alone, there is a high detection rate for heart failure, but the population level results, there is no improvement, which is because the clinicians are not tend to use these AIs because they are not in their workflow. And also regarding building a safeguard of our generated AIs, the AIs must ask for human permission to operate on some certain actions. And also regarding the patient-centered AI deployment, I'm interested in extend the patient-centered care delivery to other sorts of healthcare, such as the ED, and also interested in the question whether we can build a patient and agents that understands across my medical records and communicates within my personalized context. Again, I want to examine whether AI system can discern the knowledge of users and generate recommendations that appropriately account for the user preferences. So another sad story, if we use LM alone for diagnostics, they have really good accuracy. If we ask the general public to use the LM to diagnose, very, very low accuracy. And also whether these kind of AI-enabled comprehension are related to certain outcomes, for example, hospitalization, emergency care, or the use of preventive services. And finally, I will keep on constructing medical AI evaluation environments that will including open source curated benchmark as well as the sandboxes across different clinical workflows. And finally, evaluate whether and how medical AI will change stakeholders' behavior, given that there is some proof that LM could, or just AI, could increase dishonest behavior. And would that be a future where we can see defensive medicine caused by the use of medical AIs? And with that, here's a summary of today's talk. Basically, I have talked about our works on multimodal medical AI development regarding MOME for clinical decision support, the RexPlan system for patient-oriented care delivery, as well as CES for pre-deployment sandbox for medical AI development and deployment. And finally, I want to, of course, acknowledge my wonderful advisors, collaborators, mentees, and I want to emphasize that multidisciplinary research has always been my passion, and none of these works are possible without these people come from different fields. And thank you all for having me. I'm happy to take any questions.